Hello everyone, welcome to my channel. In this second informative video series today, I will tell you a little bit about the terminology of this program that we use. We will try to understand how a concept that we will often pronounce when using this program can direct our design thinking rather than the form of a mathematical expression. You may know that I have some Rhino development videos for you on this platform, and my goal is to expand your knowledge with different topics that I know a thing or two about through these videos. One of them is NURBS geometry. Let's talk about a concept that is pronounced so often, and here I'm going to give you a brief introduction to that magical world. So if you're ready, let's get started. Whenever we let go of our rulers and look through the window, there was a whole world out there everywhere around us of seemingly random free-form geometry. If you have some clue about NURBS, you will know that non-uniform rational B-spline surfaces and curves are a set of polynomial equations that can be used to model in theory infinitely precise free-form geometry. Any shape you can imagine, very simply said, since the very early human history as our knowledge got molded and shaped by peoples like the ancient Egyptians, or later the ancient Greeks, or later non-ancient people. We developed mathematics and geometry, which we could use in architecture to represent model, and eventually build objects. However, we were usually very limited with simply these simple discrete lines or regular shapes like circles and arcs, and much later we managed to develop functions in order to describe regular 3D bodies, like spheres, cylinders, cones, toruses, and so on. But whenever we let go of our rulers and look through the window, there was a whole world out there, everywhere around us, of seemingly random free-form geometry that we could model in clay or in marble, but not really mathematically described. So how could we do that? We used functions to describe regular bodies at the same time. We were all aware of the general behavior of functions since our elementary school with functions. As we let one of the variables change, we can plot the result of the function on a graph. But it was very hard, if not impossible, to do that. Backwards to take a stone and say, how can I create a function that once I plot its graph, I get exactly this surface? And with NURBS geometry, we kind of managed to do that. Most of the credits for developing NURBS goes to two people, whose names? Pierre Bézier and Paul de Castro. Not surprisingly, both of them worked for car manufacturers. The first one for Renault, and the second one for Citroën, famous French car manufacturers. I say not surprisingly because industrial design was definitely hungry for mathematical description of free-form shapes, much more than architecture. Gaudi was somehow managing without it, but there weren't that many Gaudis back. You might already recognize the name Bézier from Bézier curves in some programs like Photoshop or Rhinoceros. De Castello's name is not so familiar, but we will go through a very important algorithm that bears his name all in all from the ship industry over car manufacturers. The end of 1980s and the beginning of 1990s introduced commercially available CAD packages with NURBS geometry inside. It first appeared in software like CATIA many years ago, and then in the recent decades became very popular through a Rhino. But nowadays it is integrated in many, if not most, of the CAD software. Open NURBS sped up that development a lot. Now here is the deal. NURBS is a mathematical formula, a polynomial, theoretically infinitely precise. I could zoom and zoom infinitely and always see a curved, smooth surface. This is how it looks in Rhino, a simple NURBS surface. But do not be fooled. What you're looking at right now is actually a mesh. It is a rendered mesh. A computer cannot show you an infinitely precise surface. In Rhino, you have two following commands: show render mesh and hide render mesh. If we show our render mesh, we can see what Rhino is using to render the shape on our screen. Visualization has to work with meshes. It has to discretize the surface, somehow tessellate it, that means. Divide it into discrete, infinite elements. Because as I said, it cannot show an infinitely precise surface on your screen. You don't have an infinitely strong computer. That is why you have the mesh setting in Rhino. Check it out. If you go to Options Mesh, you have two options. When we change it, our mesh changes. If you have a faster CPU or GPU, you can work with smoother meshes, meaning meshes with more faces. But if I draw a vertical line and search for an intersection with the surface, the intersection will be calculated with the surface, not with the mesh, with the mathematical formula of the surface, so it will not be between the line. To talk a little bit more about NURBS and summarize, since NURBS is a mathematical expression, we can set how it appears on the screen. But the product to be produced can have a perfect curve. Non-uniform rational B-splines, NURBS, is simply the name for the mathematics that is used to create the geometry in Alias and in many other CAD systems. Luckily, no understanding of the math is required to become an expert Rhino user. There are a few technical terms that are used for controlling the shapes we design, but they are simply learned as each tool is learned and don't need to be understood in a mathematical way. If you are interested, however, a useful overview of NURBS modeling and mathematics is given by Stephen M. Hollister. The key benefit of NURBS is that it isn't an approximation of a smooth shape. The math calculates an accurate definition of the surface shape, which is still smooth, however closely the surface is examined. How NURBS are used. A NURBS surface is defined by a network of control points. The position of the control points pull the surface patch into a shape, like a flexible sheet. The key skill that you will develop is choosing the right number of control points and the right position of each of them to achieve the sculpted surface shape that you need. According to control point number, we can design shapes and transition of the surfaces. Comparing traditional modeling to NURBS modeling. A useful way to understand how the NURBS geometry works without needing to understand the math is to compare it to the traditional way of creating large, smooth curves using physical splines. Since we're mostly going to be working with NURBS modeling and Rhino, let's look a bit more at the background of NURBS. NURBS stands for non-uniform rational B-splines. Don't worry, you don't need to memorize that, but it's a neat party trick if you remember it. But let's look at what a spline is first, because that is important for our work. Here, splines are types of curves that were originally developed for shipbuilding in the days before computer modeling. Naval architects needed a way to draw these smooth curves through a set of points. And so the solution they came up with was to place metal weights or knots at the control points. So remember this word, as we'll use it a lot when we work in Rhino control points. These control points are what they used to bend the metal or wooden beams, or splines. The physics of bending a spline meant that the influence of each weight was greatest at the point of contact. So the further away you would move the weight, the smoother the spline became. Okay, so now think of these weights as control points. And let's head back to Rhino. When we create curves, we specify the degree of the curve. So think of this degree as a weight. The closer the weight to the curve, the greater the point of contact, and the more influence it has directly on the curve. Okay? Let's see this in action. Let's draw 3 different curves with different degrees. Here we have degree 1. And so we're basically drawing a polyline degree 2. Now we notice how the curve softens and how much further the control point is from the actual curve. And with a degree 3, we can see that it's even further away. Now I will select these curves. I'm going to switch off my gumball, switch my points on, and I'm going to switch my gumball back on again. I will explain a bit later how the gumball exactly works. But here I am just dragging the control points up and down, so you can see how that affects the curve. Remember that in the digital world, our control points are our centers of gravity for the lines. See you soon.